Thank you for including me in the schedule today. My name is Brendan Farrell from Clockwork Micro, my own tiny little company. We're a couple people based in Seattle, but for this school year, I'm in Paris with my family. So I had a project come up just a couple months ago, and it presented what I thought was an interesting little question, like kind of nice and easy to state. So the title of the talk is Mapping Where the Data Is Not. The question came up related to FEMA flood maps, which is something that I work with quite a bit. And so in the United States, the government develops maps for flood risk, and then based on these, they affect the insurance that people have to get for their homes. And the U.S. government, there are 3,200 counties or so in the United States. The U.S. government does this by county, and they're continuously updated. And of course, most area is not in a flood risk area. You know, a lot of areas just, of course, elevated or something that makes it not in a flood risk area. So you're talking about, you know, a small percentage of the country, like in the single digits, is considered a high flood risk area. So for the company that we were working with on this, they want to show where a region is considered a high flood risk. But the implication is that areas that are not shown, with some sort of polygon or some sort of visual, areas that do not have this indication are then considered to be not in the flood risk area. But there are areas that have not been mapped at all. And so how does a user looking at a map tell if the area has been mapped or not? The areas that have not been mapped are relatively small. It's a minority of counties, but it can be even parts of counties. But you'd like to know, has the area been mapped or not? And so they wanted a designation for the areas that have not been mapped. So that's the question. Show on a map, on a visual, like a web map, the areas where whatever data it is that you're looking at do not exist. So find the complement. And then, of course, there are some little, tricky items to that. So you want to, it has to have some sort of data of some kind, some sort of tag that allows you to represent it or color it or, show it in some way. Well, I suppose that's the most important thing. And then the other question is then, well, what's the complement? So if you have a project that is, not evolving or not too big, you can always just take the complement. So if you have, say you're looking at one state and you've got a study, or you've got a region of the state, say, that has been treated and has been partitioned into areas that are, say, in this case, high risk or low risk for flood, then you could always just take the complement within the larger polygon, and then you'd have, in a sense, you could add it to your original, or you could keep it as a separate one. It's okay, well, this is the data for the regions that have not been mapped. Those are options when you have a data set that's not evolving, or say not very large, and when your complement is well defined, but it's not a general solution. So if your data is evolving all the time, you don't want to always recompute the complement. You may not even want computing the complement could even, it could be a very large amount of data. So essentially on the fly, the idea is show areas where the data is not present. So that's the challenge. It's not a big one, but I thought it was kind of interesting because I hadn't considered it or heard of it or thought about it yet. So that's the motivation. That's the problem. It's I would just like to propose one. I think the problem's interesting, so I'd proposed it for the it's just the nature of the question. But after that, I'd like to make some comments and show one solution in this setting. Okay, so like I said, this is an example of showing the complement of the data on a map, in particular when the complement is large or evolving, that type of thing. Okay, so we want an example to work with. The one that I had with the floods is got some more details to it. I wanted to strip those away. And so here I just took a simple map. This is the states of India, and I'm interested in a visual display, so I will use vector tiles for that, and pulling them from postgis. And so basically I want to create vector tiles, and where the data is present, I would like to present the data. In this case, the states of India, and they each have a name field. And where the data is not present, I just want to put some sort of display. So in this case, I say, the name is out. So that's the basic goal that we'd like to address. So it's just essentially talking through a SQL query and how it works, and pointing out a couple of things to keep in mind. All right, so I wrote this in our meaning, Clockwork Micros. We have a little GUI tool that allows us to create an endpoint that delivers vector tiles from a Postgres database based on a query. There's the tiniest bit of formatting here where the bounding box is communicated to the query, but other than that, everything else is very perfectly standard Postgres. So could be adapted very slightly and used elsewhere. So there are a couple interesting items, I think, that I had to think through when looking at this. So here we have a tile. The tiles are these squares, and then we have several cases. So let's look at. First, I'll look at the cases where, like I wrote here, where there's an intersection. So, a vector query is based on a bounding box determined by, the vector tile format. And then, so when the tile intersects the data, in this case, so this tile here, this larger square, and when that occurs, we want kind of like to handle the two regions separately. So in this area, this is within my tile, but outside the data, I'd like that to be considered, region, like the outside region, and handle that properly. And then this is the inside region, and I'd like to handle that properly. The second, case, I don't mean cases in terms of the SQL query, but the second, case in the more general sense to handle is when the vector tile does not intersect the data. And so in that case, you want to just attach the tag that you've chosen. So when we have this intersection, we would like to deliver this outside, and then we have to deliver the inside, but we have to be a little bit careful. So when they intersect, when there's an intersection between the tile, what geometry do we return for the outside? For the outside, we return the difference, right? So we take the tile, the bounding box, and we remove from it the data. And then there we attach this field out as name. So that's where I'm sure there's better ways to do this, or at least other ways to do it, but this is how it seemed to me the most straightforward. So for that case, when there's an intersection, I take the difference. So this is now the complement of the data within the tile, and I attach the name field. If I had other dummy variables, I'd have to, right? If I had other variables that in this case would now be empty, I would have to list them there, or fields, I should say. If there's not an intersection, then I return just the bounding box. And this was necessary. I had not used this feature before, or this had not yet come up for me before, but when you take the difference between, a geometry and then then an empty query, or a query that doesn't return anything, you get an empty response. That surprised me a little bit. That's probably its own little topic, why that works that way. But that's what I found. And so you cannot just take the difference even when this is empty. So even when there's no intersection. So you need this case. You can't just take the difference and just remove it. So you need to break it into these two cases. That's, like I said, I may be wrong and I'm not using the difference function in the optimal way, but that was at least how I found it in my understanding. So you cannot just subtract the data, because if there is no data, the difference function will, in a sense, fail and return an empty response. So you need to check, is there an intersection or is there not? So now in this case, or in this top part, we're returning the complement when there's an intersection, and when there's no intersection, that is to say out here in this square, we're returning the bounding box. Polyunion is the union of the data from within that tile. So you have a little with clause up above to extract that. And now we take the union with the data. So then when there is the intersection from the original table and the bounding box, then we return that geometry and here the name field. So that's essentially like the SQL query, or the kind of thinking that you have to implement, and that returns basically these three regions, right? Outside there exists data, but you're in the complement, and then when there is the data. And so I'll just show kind of the auxiliary pieces to the puzzle. Here's the bounding box, which is necessary for the vector tile. And then I've created for the original table, I've taken the intersection, right? Because otherwise these can get so large that you're looking at if the data set is large, that's well, the query takes much longer. And so you want to run an intersection first on just the tile that you're interested in and only work with that. And here, so polyunion is the data within that intersection. So first, I like to break these things up. I find it easier to follow them that way. So I've created this original table, which is just, it's the data within the small box. And then here I've taken the union of that data, right? And then I use that for the difference. So that's how we create the data. And then here we create the vector tile geometries, and then that's returned. And our GUI, which I wrote this there. Using it allows you to kind of see it as you write it. And so here we get this display, and you can see how okay, so in this case now the tile is much larger. Here we're outside, and then there it shows the states, and then again we're outside, and it of course would go for the whole world. So this is an example where if you were working in let's say India, and you wanted to show the complement, if you use the entire globe and compute it in one sort of static manner, I mean one could do that, but I don't know, then you run into other difficulties, like from my point of view. So I find this to be a nice approach, and in particular, I thought it was interesting how you had to break it up into these three groups, and then paste them together. And you need to pass the name. So there are these tiny items to keep in mind, right? You can't just take the complement and then if we had other fields here, like say it was the population or some other field, you can't just have the complement not have the same format. They have to have the same format, and then they can be displayed and treated in the same way. So I will That's pretty much it. I wanted to just present this interesting question and this answer, and hopefully someone else down the road will come across this and find it helpful.
All right, thank you very much, Brendan. And I'd be interested, people in the chat, if you have your own story of finding the opposite of where things are. I definitely have mine. For me, it's generating ocean polygons, because inevitably you have data and the data is tied to the land. And if you have any sort of desire to render the ocean separately from the land, like to do something other than just make the background blue and paint on top of it, you need an actual ocean polygon. And yeah, that involves taking everything which isn't ocean and unioning it together and then subtracting that from the rest of the world. And what you get back out is the ocean. Not done tile by tile, usually done in a whole data set. I like the idea of doing it tile by tile, because potentially then you can make it a little less of an unconstrained problem. The problem with the ocean polygon, if you do it in its entirety, is that you end up melting, all of your data together into a union, which can take a long time, and then subtracting all of that from one ocean polygon, which also can take a very long time. So I love the idea of doing it tile by tile. I guess you're doing it here for live display, but just as a data processing trick, breaking the problem up into tiles would make it a lot more tractable from a memory and CPU point of view.